So I'm going to turn to the notes, and it's called numbers. Is that what you have there somewhere? The notes will be slightly different for you in that because you're looking at this in A4 as a set of notes that you'll use. I'm using this in PowerPoint presentation, but every line in it, every example in it, every question in it is the same. Is that okay? So we're following exactly the same question. So that's it. You've got numbers there. It's called arithmetic at the start. So ready to start? And what we'll do is we'll break this session up as well into a few parts. So if you're looking back on the video, you can just look into the various bits that you need. You'll have the notes anyway, and you can jump to the bit that you want. So, okay. It's a few minutes to start past starting time. Very gentle, nice, easy start. You've got out of bed, you found your way here. So let's do a nice, gentle first session in numbers. Okay, this session talks about numbers and the basic operations in them. Well, when you learned a language, you started learning the alphabet, A to Z. And you had both capitals and lowercase letters. And you used this all the time. And later on in the language, you started putting in punctuation marks, full stops, commas, colons, semicolons. And that's the language that you use all the time in English, or in whatever your first language is. Mathematical symbols are much the same. You start off with 0 to 9, and you learnt those in primary. You learnt some basic operations, plus, minus, multiplication, and divide. And then we added a few more, plus or minus, greater than, less than. And they became sort of concepts towards secondary school. Pi, e, exponential, infinity, and a whole load of different things. And then more recently for the Leaving Certificate, all these trigonometric functions, the cos, the cosine, all of these. There are other symbols as well on your calculator, log to the power of 10, natural log, and dy dx, which is on your course. And there's a whole load of symbols here that you used for sets. A intersection B, the overlap in Venn diagrams, and you used all of these things. And then you had these fancy letters for number sets. And you had these sort of strange symbols as well. So, just imagine that not every one of these is common to you. Imagine if that happened to you in English, and that when you were way back in learning your English language, you were sort of found some of the symbols a bit more awkward than others. You didn't grasp every single one of them. So let's imagine that you were out when the teacher did the letter T. You missed that day in primary school. You never learnt the letter T. You learnt all the other letters, you could get by. You could have a dog, but you couldn't have a cat. You could live in a house, but you couldn't live in a flat. And you could drink coffee all the time, because you just never got the letter T. Now that seems a bit sort of mad, really. It's a bit far-fetched. But there are people who miss math symbols. And maybe one or two of the symbols, like the factorial symbol, or the cubic root symbol, or the log symbol, might be just unfamiliar. If we go back to English for a moment, there are people who maybe missed out on the fine uses of semicolons, or colons, or when do you use double quotes, and when do you use single quotes. You might have been out that day. And if you're out someday, what happens is you have to go back and say, oh yeah, fill that in. And when you do go back, you'll find, actually, it's no big deal. It's just another letter. It's just the letter T. Oh, now I can have a cat. Or now I know that double quotes are when you're paraphrasing somebody talking, and single quotes are just when you're highlighting something. And you get that, and you say, is that all it is? Oh, fine. So basically, what happened along the way, most likely, for everybody here, is that throughout your primary and secondary education, at some occasion, you missed one of those simple steps along the way. And it's now the job to put those back in. I give the analogy of Hansel and Gretel. Hansel and Gretel is a story where at one stage they were taken by their father on the wish of the stepmother out into the forest because she didn't want them around. And they found the way back because they had dropped a few stones along the way to find the path. Now, the second time they didn't have the stones and they couldn't find the way back. But maths is like that, a series of stones. And if you find that you missed one, or you were out the day when they did one or two of the stones, it means that there are patches when you're walking through the maths course that you just can't get from one to the other. And maybe to date you've written that into your own mind as being, I'm no good at maths. Or maybe all it is just that you're missing that particular stone, that particular letter, that particular symbol, and that it's absolutely no more difficult than all the other stuff you've learned anyway. And you just need to connect it up. So that's really what we're doing. We're going to take those gaps. And with the resource online, it means that you don't have to go through everything from start to finish again. You don't want to do that. You know most of the circle, most of the line, most of calculus, most of everything. But there's a couple of pockets where you're not so sure all the time. You go back, you look it up. That's what it is. IFI, now I'm comfortable. So let's now look at how maths works. These are things you've done along the way. And we talk about the order of operations. When they started writing symbols, somebody had to figure out, how would they actually be interpreted and used? And they came up with this BIMDAS method. In Ireland, we call it brackets, indices, multiplication, division, addition, and subtraction. If you were in high school in the States, they'd use the term PEMDAS. Parentheses, exponents, multiplication, division, addition, and subtraction. Or in any textbook in the US, they'd say, please excuse my dear Aunt Sally. It's pretty lame, but you get the idea. It just remembers the order. So parentheses are first. And it means that when you're doing a question, you decide which is important. So we're going to start with the first question. And here we want you to calculate 3 plus 2 by 4 minus bracket this by this. And this is where BIMDAS and PEMDAS comes in. You've got to work out from that, and hopefully you have a pen and you can write it on the page now beside you, which one comes first? Do we do 3 plus 2 and then multiply? Well, if we look at this on the BIMDAS, it says that you must do what's in brackets first. Then you do any indices if there are powers. Then you do the multiplication and division, then the addition and subtraction. So I leave you with that question now. Just to write down, just take a minute to do that question and see how you'll get on that particular step. Okay, so we'll give that a go. The first thing we see along here is that the 6 divided by 2, they're in brackets. So we have to sort out that. So we're writing it out again just to start, but the 6 minus 2 divided by 2 there, because that's in brackets, we're going to deal with that first. So 6 divided by 2 becomes that 3 there. There was a minus beforehand and it stays minus. Now after this, in step 2 there, you see that 7 squared? We've no more brackets now, but we have this power this exponent, this indices. So we're going to go with that 7 squared and get rid of it to 49. The next step then is we've got all those right. And we really have quite a simple, straightforward 3 plus 2 times 4 minus 3 plus 49 times 2. But the rule says BIMDAS. And it prioritizes multiplication and division over addition and subtraction. So therefore, when we see this 2 times 4 and 49 times 2, they get done first. So that's our 8 and that's our 98. And then at that stage, we just do it in order. 3 plus 8 minus 3 plus 98, etc. Now, there will be questions like that. Not just do this. Here's a question, please simplify, though it may be there. But in all of your calculations, you're going to have things that you're going to have to bring together. And this fundamental convention on which ones come first, you need to know. So here's another example now with simplification. Might just give that a go for a minute. Okay, we'll do this now. We look across, and the first thing we see are the brackets. But within the brackets, we actually see there's powers within the brackets. So we now focus our attention on the 2 squared minus 1, and the 2 squared must be done first, so that becomes 4 minus 1 within the brackets. So nothing else has changed. It's the same line as before, and I've just changed that to 4 minus 1. The next line then is, well, I still have the brackets, 4 minus 1. That takes precedence. 4 minus 1 is 3, and that solves that. Now I look across, and I might get rid of the brackets, all right, but I've got this power, because that's really 4 times 3, that's multiplication, really. 3 squared, that's 9. So I've got my 9 and my multiplication sorted, divided by 3. Again, I look across, and I say, well, I've got addition, that's easy. Subtraction, that's fine. But the division is first, so that becomes the 4, and then it gets solved. So that's that step, really. That's BIMDAS and PEMDAS sorted. We're now going to look at numbers and factors. So, numbers and factors. Factors are integer values that go in evenly, divide evenly into another integer number. So we might have something like 12, and the factors of 12 are 1, 2, 3, 4, 6, and 12. If you have a pizza with 12 slices in it, or 12 eggs, or 12 anything, you can divide that amongst these number of people in an even number without breaking any of the particular units. Here, 18 would have different factors again. Sometimes the expression can be simplified. So you might get a factor of 12 over 18, and that's 4 over 6, because there are 3 4s in 12 and 3 6s in 18. But how do you know you've reached the end of this? Could it be simplified again? It could be 2 over 3. But could we go again? Do we always know? It's easy if the numbers are sort of small. But what happens if the numbers are in their hundreds? Do we know if it can be divided again? So you learned something way back called the highest common factor. And here we've got the factors of 12 and 18. And we said the factors of 12 are 1, 2, 3, 4, 6, and 12. And 18, 1, 2, 3, there's no 4. Because 4 into 18 goes 4.5, so that doesn't count. 5 won't go in. 6, 9, and 18. And if we look across here, we say, well, where is the one, the highest one, that they both have in common? Well, they both have a 1. That's not much good to us. 2, yeah. 3, yeah. 4, no. But 6, they both have 6s. They don't have anything else above that. So it looks like the highest common factor is 6. So if we were to take the 12 over 18 and divide each side by 6, we'd get to 2 over 3. And that would be the smallest, simplest, purest way to represent that factor. So here we get a question now, and we say, okay, here's a factor. Express 160 over 1,000 in its simplest form. Now we could do that by writing out all the factors of 160 and indeed of 1,000. But that seems like a long way to go. You know, it really, you'll be there for a while. What happens if they said 4,000 or 43,000? You'll be there forever. So there must be other ways of doing this. So we might be used to say, divide everything by 10 and see where you go then. But the highest common factor here turns out to be 40 and 40. They both have a 40 and nothing above that's common. The 80 and the 160 are not represented here. So we could divide it by 40. We could get 4 over 25, dividing both sides, and that would be correct. But for most of us, that would be some hell of a job to work out all of that. And what we've learned over the years is to make it much easier. So we do it step by step. We take the 160 and we say, look, it's sort of clear that they both have a naught at the end. So if we got rid of the naught, it might be easier. So let's divide everything by 10. And that gives us 16 over 100. So we just took out a naught on both sides. Then we said, okay, let's go again. And we say, is there anything else on the 16 and the over 100? Well, they're both even numbers. So divide by 2. And that gives us 8 over 50. So let's look at that again. We go again at the 16 over 100. We divide it by 10. So if we go again then, we say 16 over 100, they both divide by 2. So 8 over 50, 16 over 2 is 8, and 100 over 2 is 50. But that looks like it could go further again, because they're both even. 8 over 50 divided by 2 is 4 over 25. And that seems to be the end of the line. And it is what we got the last time when we went for the highest common factor, but we got it a lot quicker. We can also check by looking at the factors of 4 and 25, and you can see that they have nothing in common other than 1. So we're there. So we'll now turn to ratios, fractions, and conversions. I'm going to just take an aside out here. At some stage during the day and tomorrow, I'm going to say things that you'll say, good God, does he think we're, you know, why is he insulting me? We know that stuff. Is that okay? Now, I actually know you know that stuff. Is that okay? But sometimes if I show you something that you know, and then use it in a different context, you'll say, oh, I didn't realize you could use it for that. Oh, I didn't realize you could use it for that. Oh, that's cool. So as they say, when I say something that's very simple, okay, please understand that, as they say, I don't think you're a retard or anything like that, that term that's used. I'm not a retard, you know. I know that. I know that absolutely fully. Is that okay? But sometimes when you see something in context and you see it again, you say, didn't realize you could use it for that. So what I'm going to do now is I'm going to show you 3 parts of your course. In fact, 4 parts of your course. I'm going to show you ratios, fractions, percentages, conversions. And we're going to throw in percentage errors on that. 5 parts. We're going to solve them all the same way. And you're going to realize, oh, I didn't realize they're all connected. Oh, all the same with that. Didn't realize that. Is that okay? So when I say something, I just want to say that so don't mind when I say something. Say, God, you know, give us a break here. Is that okay? So I'm just letting you know what you do know. Is that okay? So we'll cut that out of the video. Is that okay? That's what we do. That's the great thing about being able to have the recordings. You can sort of pretend it wasn't like that at all. Ratios, fractions, and conversions. Ratios and their properties. Well, a number like 3/6 can also be described as 1/2. And you're used to that. If you split a pizza in 6 and somebody takes 3 bits and somebody else takes 3, they get half each. Very familiar. There's the 6/6. There's the 3/6 and the 3/6 by joining them together. And effectively, it's half and half. So you're very familiar with that. Let's use that insight for the moment and see if we can push it and use it to our advantage. 3/6 is 1/2. Can we prove that that's correct? Well, if I want to prove that one side of an equation is the same as the other, this is how I do it. I say, is 3/6 equal to 1/2? So if I want to prove if 3/6 is 1/2, this is how I would do it. On the left-hand side, I say I don't like the 6 on the bottom. So I'm going to multiply by 6 because that's dividing at the moment. And if I multiply both sides, then it'll be easier. I'll get rid of that division. So I get 3 is equal to 6 times 1/2. And that's 6/2. And 6/2 is division, and that's 3. And 3 is 3. So that ratio does work. 3/6 is the same. 6 is 6. There's an alternative method of doing that. It's called the cross multiplication method, where if somebody says 3/6 is 1/2, you're very familiar with cross multiplying. 3/6 is 1/2. That times that is that times that. Top right, bottom left. Top left, bottom right. So you say 3 times 2. 3 times 2 is 6 times 1. 6 is 6. And again, you get that equivalence. What I'd like to do now, though, is to show you a technique that's the same as the cross multiplication, but I'm going to put it in a nice 2x2 4 situation box. So a 2x2 box. 3, 6, 1, and 2. 3, 6, 1, and 2. 3, 6 is a half. If I read this horizontally, I could look at the equation like this and say 3 is to 6 as 1 is to 2. 3 cans of whatever drink for €6, 1 can for 2. 3 bananas for 6, 1 for 2. I could decide to read it vertically 3 bananas for €1, 6 bananas for €2. It seems to be sensible in both directions. And if I were to do it diagonally, 3 times 2 is 6 times 1. So let's look at that again. 3 times 2 is 6 times 1 if we took reading diagonally. If we read vertically, 3 over 1 is 6 over 2. I'll write the numbers again. 3, 6, 1, and 2. So horizontally, it's 3 tickets for €6, 1 for 2. This way, 3 for £1, 6 for €2, 2 for £1. So you can read it vertically, horizontally, or diagonally in the box. Let's see if this is generally the case. They were just 4 numbers. Let's do it for algebra. A over B is C over D. We could draw those in a box if we wanted. A, B, C, D. And we could say A is to C as B is to D. A is to B as C is to D. A times D is C times B. So cross multiplication, we would say AD is BC. You've done this a million times with cross multiplication. Also, if A over B is equal to C over D, then also AD is C over B. But let's do some step-by-step multiplication on this. A over B is C over D. If I wanted to solve that, when the question is solved, on the left-hand side, you just have a letter. You've no more junk over there. X is 2, Y is 7, A is something. You don't have another thing on the bottom here. So the only way to tidy that up is if you're dividing on this side, you multiply on this side. So you multiply on that side, and they cancel. And you get A is equal to BC over D, which is what we get here. Now, another way of doing that is, I don't like this D on the bottom. How would I get rid of a D on the bottom if I wanted to? I could fool around with the same equation and say A is equal to BC over D. If I wanted to get rid of that D on the bottom, well, it's dividing, so I'd multiply. And I'd get AD, or DA, they'd cancel BC. So that's proof, really, that if you start with A over B is C over D, you end up with the cross multiplication formula proved. Great. What does that all tell us? Well, let's go one step further. Let's imagine that AD is BC, because we started with A over B is C over D. So we've now got AD is BC. But if this is the case, I'm now going to divide this time by C on both sides, and I get AD divided by C is BC divided by C, and I'll cancel those. AD over C is B. And if I divided this by D, and this by D, they'd cancel. And I'd get A over C is B over D. What did I start with? I started with A over B is C over D. I've actually changed. Instead of having A over B, I now have A over C. In other words, that if I draw any box at all, and I say A, B, C, D, if A over B is C over D, I'm reading horizontally. But I've also proven that if that's the case, vertically, A over C is B over D. And also, diagonally, that AD is BC. Why was I doing that? I'm doing that because this will crack every single possible question for you in your paper on ratios, on conversions, on fractions, on percentages, and on percentage errors. So 3 over 6 is 1 over 2. We've got horizontal sense of that, vertical sense of that, and diagonal sense of that. Now we're going to start benefiting from that proof. So we ended up in the end that A over C is B over D, even though we started with A over B was C over D. Using the tabular technique to solve a question. Very often in the exam, they don't give you the 4 numbers, they only give you 3. So one of the values will be unknown. So here we're starting with fractions, and they say 3 over 9 is x over 12. We're going to write those numbers in 4 boxes, 3x, 9, and 12. How could we calculate x? Well, there are a number of things we know. We know that the box makes sense this way, and this way. We can pick any one we want. So I'm going to do the standard one that you learned, called the crossover method, like that. And we say this times this, top left, bottom right, top right, bottom left. And we'll say 3 times 12 is x times 9. So we get 3 times 12 is x times 9. 36 is equal to 9x. If we had 36 is 9x, how do we find out what x is? Well, we do it most ways. 9x is 36. I would like x on the left-hand side on its own. What is this number? 9. What's it doing there? Multiplying. How do I get rid of multiplication? Divide. If I divide on one side, I divide on the other side. X is equal to 36 divided by 9 on a calculator, 4. Is it okay? So this is the question now for you. Or maybe I'll do this one and then leave the second one to you. You have €200 prize between 3 candidates in the ratio 3 is to 5 is to 2. So you all shared in some lotto tickets or something. Some person bought 3 of them, one person bought 5, another person bought 2. And you decided that if anybody won, you were going to share the prize. And €200 came in. Divide that 200 now in the ratio 3 is to 5 is to 2. Now before you do, imagine that the only technique you had was this grid. You had to write it in this table. Well, how would we do it? Well, what do we know? We know one thing for sure. 3 and 5 and 2 is the total of everybody bought. So how many tickets did they buy between them? There were 10 tickets. That was the total number of tickets. And what was the overall prize? 200. So the 200 in a way went with the overall 10 tickets. You've got to figure out how much does this person get, or this person get. Is that okay? So this is our x. So this is the way we do it. We write down and we say, well, the total, what do we know? We need to know 3 of the 4 things. We know, for example, that there were 10 tickets bought. We know that there were €200 in the prize fund. And we want to know what 3 parts, 5 parts, or 2 parts would be worth. What would that be worth? So what I'm going to do now is I'm going to take subsections of that, and I'm going to start with just the first bit. I'm going to pretend that the other 2 bits don't matter for the moment, and I'm going to say, what does the person who bought three tickets get? 200 is to this as X is to that. What is that value? Now, before we do this, I want you to also think like this in the exams, and that remember that you're good at maths and you have a good idea what the answer will be. I'll show this so many times in terms of probability and statistics. You get it. You understand what the answer is expected to be before you even touch the calculator. If there are 10 people and they win 200 between them, 3 people will deserve some of that 200. This number here has to be less than 200 because 200 is the total between 10. It's not going to be 6pence or 6 cents or €3,000. It has to be of the order a lot less. That 3 is about a third of 10. So that's going to be about a third of that. So before you even do the calculation, you know it's going to be about, I don't know, about a third of 200. What's that, about 66 or something? You know that that's the answer. So before you go click, 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 and the calculator gets 17.6 because you hit a wrong button or you were nervous or something, you know it can't be 17. You know it can't be 5,000. It's got to be in the scale of things and less than 200. So that's the grid there. And one way of doing it is that. So 200 by 3 is 10 by x. So you say 200 times 3 is x by 10. 600 is 10x. 10x is 600. Now that's the equation. If ever I see an equation at all where you've got 10x is 600, any equation that doesn't have the x on its own on the left-hand side, I've got to sort that out. That's a multiplication, so you get rid of multiplication with a division. That gives you x is equal to that's divided then equals 60. So that's how much this person gets. That person gets €60. How much does the person with 5 credits get? Well, 5 of 10, what's the ratio there? 5 is half of 10, is it? So we'd expect this to be half of 200, wouldn't it, before we even do the calculation? We expect that to be 100. Do the calculation. 200 times 5 is y times 10. 1,000 is 10y. 10y is 1,000. Y is 100. Same calculation. And the third one, the value for z, the person who bought 2 shares. 2 is a fifth of 10, so a fifth of 200 is 40. But 200 times 2 is z times that. That's 10z. 10z is 400. Z is 40. And the ratio then is 352, x, y, z, 60, 140. And they add up to your €200. Okay? Question 2. Leave this for you. €15 represents 3/7 of a particular prize fund. What's the total prize fund? Okay, let's continue. Example 2, ratios. €15 represents 3/7. What's the total prize fund? Well, when I do those, I draw the 4 boxes. And I say, okay, I've got to equate them in some way. And I say, well, 3/7 is 15. I happen to be reading them across. I could have said them vertically, but I'm using it across. If 3/7 is 15, what's the total? And how many 7s are there? 7. So 7 is known. So really what you're saying, if 3 is 15, what's 7? And this becomes your what? That's the thing you're looking for. And once you've drawn them in that order then, all you have to do is simply crisscross. So you say 3 times x is 7 times 15. 7 times 15 is 105. 3x is 105. And how do you solve that? That's multiplication. Both sides, x is 35. Next example. All of these are examinable. All of these are typical of what's come up. Express 60 milliliters as a fraction of a litre. Give your answer in its simplest form. So what you've got to do here is you've got to draw a box again, as always. And you've got to say, I know something. I know that 60 milliliters is something. So therefore you can write that one way, either vertically or horizontally. And then you say, what's a litre? How do I do that? How is 60 a fraction of something? So I'll leave that with you for a minute. Give that a try. Okay. How do we solve this? Just bear with me a sec. Example 3. Express 60 milliliters as a fraction of a litre. Well, the thing to note here was that 1 litre is 1,000 milliliters. So 1 litre represents 1,000. So 1 litre is 1,000 milliliters. What would 60 be on that basis? It would obviously be less than 1, significantly less than 1, a fraction of 1. And how would we work that out? But we've written it in terms of something we know. 1,000 is 1. What's 60? Again, same 2 by 2. Crisscross them. And we say 1,000 times x is 1 times 60. 1,000x is 60. But I don't like 1,000 on the left-hand side. That's multiplication, so I divide. X is 60 divided by 1,000. And again, if we use the factors or we go through a reasonably simple method, dividing by tens and taking it down and dividing again by, we'll end up eventually getting 3 over 50. So that's fractions, really. So it's 60 over 1,000. How did we simplify it? We say get rid of the 2 noughts. That's 6 over 100. They're both even. 6 divided by 2 would give us 3. 100 divided by 2 would give us 50. 3 over 50. If I work out the factors of 50, 3 isn't one of them. So it doesn't divide it evenly. So 3 over 50 is my answer. 3 is a prime number, does not divide into 50, therefore we're finished. Now, let's use the same technique for percentages. Percentages represent a form of ratio. It's so much over 100. 50 over 100 is a fraction. It's also a percentage. So we say 50 over 100, 50 per 100, 50%, or 50 with this symbol beside it, the percent sign. So somebody says, calculate 22% of 300. Well, you know that 100% of 300 is 300. 22% will be less. So you draw the box and you say 100% of 300 is 300. What's 22%? Don't know. It's x. And you crisscross. And you say 100 times x is 300 times 22. 100x is 6,600. And 100x, I'm not really gone on. From the calculator point of view, it's 100x is 6,600. I want to bring it down to x. I divide by 100 on this side. And I get that x is 66. So percentages, example 2. I'll leave this one to you. 120 euro represents 8% of a prize fund. What's the total prize fund? You now know that 120 is 8. What's the total? Is that okay? Before I do that, I just want to say one thing about maths, right? And riding a bike and all of those things. There are 2 parts to your brain, okay? Lots of parts. But the top part up here is used to conceptualize something. You have to figure something out. So what's really going on here? And you have to figure out, things. And it takes a lot of thinking time up there to do that. And after a while, if you practice it, it actually leaves there and goes back in here into your cerebellum. And you do it automatically. You no longer have to think about it. It's actually routine. And you're not saying, oh, I can conceptually understand that. No, you need it in here in the routine. So when you were learning to walk, you were there figuring out, oh, I stand and I try this or I do that. Or learning to ride the bicycle, conceptually you're saying you have to hold on and keep it balanced and not turn over too much and go a bit faster than this and whatever. And you were trying to grapple it all in here. And eventually you did it so often that it fell back here, and it's absolutely instinctive. You get on a mountain bike, you get on any type of bike, not a bike you're familiar with, you just do it. Same in a car. People rent cars in different countries. They don't have to say, what's this about now? How do I do again? I have to use that. It's all back here. Okay? Maths is like that. Maths is actually active. It's a doing thing. And the more you do it, the more you practice. Oh yeah, that's good. That's brilliant. There's a familiarity about it. It's not, oh, I can understand the fraction stuff. You got to do it. And when you do it, you say, oh, that's... And you just get so routine at it, you can find your way around through anything then at that stage. So that's why I'm giving a number of these questions here. It's not sufficient in the exam to say, oh, I can work it out again and think about how you walk or how you cycle or how you do that. It needs to be back in there in the practice. So that's why those exercises are useful. You do just to keep the old mind fresh. But you'll be doing this between now and the exams anyway, and you're becoming comfortable with it. There's conceptually nothing difficult there because you've grasped that. But I just wanted to join all that stuff together. We're now looking at percentages. We've done ratios and we've done fractions. We're now looking at percentages, and then we're going to do conversions, and then we're going to do percentage errors. Is that okay? So I'll just leave you with that question. I'll give you this question. €120, I think yes, okay. Percentages, example 2. €120 represents 8%. What's the total prize fund? Well, if I draw the boxes here, I get that 8% is 120. Or in its simplest form, just here, 8 is to 120 as 100 is to what? And it's the same standard as always. 8x is 120 times that. 8x is 12,000, x is, divide one by the other, x is 1,500. And we look at that and we say 8% was 120, 100% is 1,500. We say to ourselves, does that make sense? Well, it does really, because as I moved vertically, the number here got an awful lot bigger as I went from row 1 to row 2. And similarly here, the number got an awful lot bigger. If I moved horizontally, the number got a lot bigger, and this way it went a lot bigger. So I was expecting quite a big number here, bigger than 100 and bigger than the 120. And I did. So it's not 3 or 17 or minus. Couldn't be a calculator error. It had to be around that. Conversions. They ask a lot about conversions in your exam. Sometimes it's minutes to hours. It might be miles to kilometers. It might be euro to sterling. It could be anything. Kilograms to pounds or whatever. And we use conversions for that. And again, there's a table. €1 is worth so much when you go to the US or you go to Australia and you're converting your currency, and vice versa. So they're used to measure this, and can we use the same tabular approach? Well, what we say here is we say €1 is currently trading at 0.87 sterling. Calculate the value of 40 sterling in euro. So over to you, do the table. 1 is to 87, what is 40? Conversions, example 1. €1 is 0.87 sterling. So again, we just write that down in the table. We say 1 is to 0.87 in terms of euro to sterling, as 40 is to what? The x and the unknown can be anywhere. If the 1 is the sterling is here, and you know 0.87 is 1, 40 is here, it doesn't have to be. It's just the way you've expressed it. So x doesn't have to be always in that spot. You don't have to force it in that. It's whatever way it makes sense to you. A euro is 0.87. What would I get for 40? So the what in this case is on this side, because that's the way you've written it out or thought about it. Again, it comes in a 2 by 2, and we can cross it. And when we multiply, we say 40 is 0.87x. 40 is 0.87x, or 0.87x is 40. Again, what have we got on the left-hand side? Well, not a lot, really. Only a number times something. But what is it? Well, it's multiplication. It's not addition. And how do you get rid of multiplication? Well, you divide by 0.87. Now, this might look a bit messy on this side, but really, it's just to divide it. So it goes away. So you get x is equal to 40 over 0.87. And this is just calculator stuff. 40, 0.87, one divided by the other, and you get 45 euro. And does that seem right? Well, You know, it probably is reasonably close, all right. When you got your euro, you got less sterling for it, slightly less than the number. Is that okay? So when you did it here, you should get slightly less again. So if you needed €1 got you less, if you wanted to buy 40 sterling, you'd need more, wouldn't you? Because if you look this way, the numbers are getting bigger this way. The numbers are getting bigger here. 0.87 went up, or you could say this went down. So this number is smaller than this number, either way you look at it. And it turned out to be 45, and that seems right. So we get 1 is to 0.87, as 45, or let's say it's 46, roughly, is to 40. Does that make sense? Well, if we look at the grid, and we say getting bigger this way, getting bigger this way, getting smaller in reverse. Yeah, I think it's 46, seems right. And that's conversions. So conversions, fractions, ratios, percentages are all the same. And percentages can also be percentage errors. It's the same tabular presentation. All of that math stuff is sorted. Okay, so we now look at scientific notation. Scientific notation is the means of writing out numbers and expressing them in a standard form. Scientists, engineers, physicists use this all the time. When they talk about the speed of light, they say something like it's 3 by 10 to the power of 8 meters per second. That's how fast light travels. 6 times around the world, I think, per second. If you take a beam of light, it'll travel around the circumference of the world 6 times in a second. Thankfully, it does, because it means that mobile phone connections and all those communications travel so quickly and instantly, which is pretty handy for us. Sound, on the other hand, is quite slow. And you can feel that you're at a football match or something, and even some part of the stadium is almost singing slightly later than some other crowd. Or sometimes if you're watching somebody kick a ball or something happening at a distance, you might see the ball being kicked, and then half a second later you hear it being kicked, because the actual sound is taking that time to travel, where you've seen it instantly. And how do you measure things like that? Things like a meter per second, and then 1,000 meters per second, and 5,000 meters per second. You can't graph those on the same graph. It's too difficult. It's too awkward. Because if you're going to have 1,000 on your x-axis, one will be so near the start you won't see the detail. So they use this scientific notation to do it. And it's very handy. It means that every single number imaginable is broken down into a format that has a 1 digit, a dot, another digit or more, and a power of 10. So here we have a number, and we say the number is 3,600. And we say 3,600, and we say, how many zeros are there? We say, well, if it's 3,600, we assume that we mean 0.000. That really the integer part of it over here, is there. And the other part is the fractional part. It happens to be 0.00. Then you say, how many places of decimal are there? And we can draw the curtains back, step 1, 2, 3, and we say that's the same as 3.6 by 1,000. Or 3 by 6 by 10 to the power of 3. So taking that in step-by-step form, what you can do here is you can say 3,600 is 3 by 6 by 10 to the 3. 360 is just the same number, but we'd only move twice. It's 3.6 by 10 to the power of 2. 36 is 3.6 by 10 to the power of 1. 10 to the power of 1 is just 10, really. And 3.6 by 10 is 36. 3.6 is just 3.6. We can also represent very small numbers, tiny numbers. Like, what do you do if you get a number like 0.36? And again, we say, well, we'd like the number on the other side to be not a 0. So we actually move this to the right now. And we say that's the same as 3.6 by 10 to the minus 1, because we're dividing. Or it's 3.6 divided by 10. Or 3.6 divided by 10 to the power of 1, or 3.6 by 10 to the minus 1, because anything on the bottom that's a positive in the power becomes a minus on the top. So what we're saying there is that we can express even this number here is 0.036. Again, we can say 0.036. That's further away from 0. And we say we better move that fella. So we say we've got to move 1 twice to get it. So it's 3.6. But we moved over to the right to get it. So that's 3.6 by 10 to the minus 2 to bring it back. So it's 3.6 divided by 100, which is 3.6 over 10 squared, or 3.6 by 10 to the minus 2. So they're all the notations there on that. And why do they want to measure that? Because really in science, and it's called scientific notation, is that some of the numbers out there are enormous. When you talk about the sort of the universe, and they talk about 10 to the 40, like 10 to the 40 miles apart, that's 10 with 40 noughts after it, measuring all that distance out there. And it's just unimaginable, really. And then if you talk about the atom, and you talk about the tiny little quarks and all those other subparticles that they found, they're talking about 10 to the minus 40. We can't even see that they're so small. And how do they communicate and get all those things together in this common number system? And that's what they do. So just ask you there to basically convert, just rewrite that number 234 as a scientific format number. Okay, 234. Well, we realize that 234 is really 234.00. That the integer part of it is over here. So we just have to get that down to just one number. So we move this way. We're moving to the left. So we say 234, 2.34 with the point now here. And because we move to the left, we bring it back by moving with the multiplication of 100. So 2.34 by 100. Or 2.34 by 10 to the power of 2. And that's it there. Similarly, the number 0.0056, how do we move that? Well, we have to get the first number to be not a 0. So that makes it a 5.6. But to make that a 5.6, I've got to go 1, 2, 3 moves to the right. And if I'm moving to the right by multiplying something, I better actually multiply then by the opposite, in other words, divide. Multiply by 10 to the minus 3 is the same as dividing by 10 to the 3. So it's 5.6 divided by 1,000, which is 5.6 divided by 10 to the 3, which is 5.6 by 10 to the minus 3. And we see it there, 5.6 by 10 to the minus 3. Now, convert the numbers back from scientific notation. Here we have 2.34 by 10 to the 3. We say 2.34 by 10 to the 3. Well, that's telling me that I've got 3 on the other side now to spare. It's really 2.34 by 1,000. In other words, I can move 3 places bigger. So 2.34 becomes 2.34, 1, 2, 3, which is 2340. The last question there is 1.45 by 10 to the minus 3. And how do I deal with that? Well, that's telling me that this number here is dividing. Anything to the minus is like saying 1.45 divided by 10 to the plus. That on the minus on the top, that on the plus on the bottom. That's 1.45 divided by 1,000. It's really saying there are 3 times you've got to shift on the bottom, and you're getting smaller. So if it's 1.45, we're going to go 1, 2, 3. So we're going to pick up a lot of noughts here to get to here. So we'll end up then with 0.00145. We can check that by doing it the other way. We can say 1, 2, 3 gets us to 1.45 by 10 to the minus 3. So it is right. That must be the right way of doing it, with all the noughts. And that's scientific notation. Okay, we now turn to a topic on rounding and truncating. You get questions like this a lot. They say you're making candles maybe, you've melted the wax, and it makes so much, you need so much wax to make a particular candle. How many candles can you make with the remaining wax or whatever? And you might find yourself with an answer like 9.8. You might be thinking 9.8, you say, well, surely that's close to 10. Well, in that case, if you've got a 0.8 left for one of the candles, it's not going to look like the rest of them, so actually you'll have to throw it all out. So you'd truncate that to 9, you'd bring it down. Sometimes you round things, plus or minus. You know, how much money do you have in your pocket? Around a tenner. You don't always drop to the lowest, the euro below it, or you can round up or down. It's to the nearest one. So numbers can often be expressed by means of their significant digits. For example, 497 might be considered close to that, and we've done that. But also then, numbers can be expressed in terms of their significant digits through rounding or truncating. I don't know if you've, imagine you're in a restaurant, 4 of you are together, and the bill comes to a certain amount. And you say it's 25.60 or something like that. Or maybe it's 27.60. You say, well, look, that's about €7 each if there's 4 of us. You round or you get some handle on it or whatever. So you don't have to do it all the time precisely. And we carry these things around in our head all the time. How much money do you have? How long will it take? About 15 minutes, about this, about that. So we are all the time thinking about rounding or approximating. So let's round now to the nearest number. Round the values 3.6 and 17.2 to the nearest number. Well, the nearest integer number is the 3.6. Well, we've got the 2 candidates on the number line. We've got 4 and we've got 3. And on the number line, 3.6 is nearer to 4 because this is 6/10 away and that's 4/10 away. So we round that to 4. Similarly, on 17.2, it's much nearer 17 than 18. So that's just the nearest one. Truncating is actually reducing it below that. So in this case, if we truncated 3.6, we were making these candles and we had 0.6 of the wax left over for one of the candles, we'd only end up making 3 candles. And the same for the 17. So let's round and truncate here. And we say, let's round the correct value to the following numbers. So 23.67345. I'd like you to round that to each of the correct numbers. I want you to do it to 1 significant digit, 2 significant digits, 3 significant digits, or whatever. Well, if I start simplifying it from the outside, well, let's say to the nearest integer number, what's that like? It's 23 is on one side and 24 is on the other. Is that nearer 23 or 24? Is it more than halfway? So this becomes then 24. Let's say I need to be a bit tighter than that, a little bit more organized, and say it was 23. So in this case here, one significant digit would give me 24. Now let's say I wanted it to two significant digits. Here I'm saying that 23, I want to know 23.67. I want to have one decimal place here. Is that 0.67 nearer 0.7 or 0.6? Is that nearer 23.6 or 23.7? Well, it's only 3 away, 0.03 away from 7, but it's quite a distance away from 6. Is that okay? So again, in the number line, if we were zooming in like you would in Google, as you go down looking for a map in more detail, we could see there that on the number line, if we were in around the number about 23.6, and we had this space here, we could see that that's actually 23.6, 23.7 might be there on the number line, and this point here would be much nearer this side, 2/3 of the way over, or more. And likewise, if we go down through all the numbers then, that's 23.7. If we wanted 4 different places, we'd say 23.673. Would we round that 3 down or up? We'd say 20.67, I think we'd say. If we had the 3 then, and we had 4, 23.6734, would you round the 4 down or up? Down. And then 4, 5. Generally, I think we might round up or round down, but we just work out on the 0.5. We're close enough on the 6 digits. The 5 is the hard one there in the middle, depending on the policy. Now, so calculate the value then of this number here and write your answer correct to 3 decimal places. Calculate the value of 1.165 times plus that over that. So 165.7. Can we express that as in scientific notation? How do we do that? 1, 2. How would we do the 44.81? And how would we do the other? So on a calculator then, we should be able to calculate the value of this and write your answer to 3 decimal places. On your calculator, 165.7 you can enter. 44.81 is not a problem for you to enter. And 1.32 times 10 to the 5, as long as you're using your brackets right, and you're not carrying stuff on and stuff like that, you should have a button that says something like y to the x there. So 1.32 times, it could be 10 to the 5 or 10 to the x. Or you could do this separately first if you wanted and put it into memory. What's 1.32 by 10 to the 5? Well, it's 1.32 by 10 to the 5. It's 5 steps to the right because you're multiplying 1, 2, 3, 4, 5. It's 13200132000.0. That would be in your calculator. But if you're familiar with the other, you just enter them all in the calculator, and we get this number here. Let's assume our calculator comes back with 0.001594772. And you're asked to write that to correct, scientifically as well, to 2 or to 3 decimal places. Well, let's look at the scientific first, and then do the significant. So I'll give you that job to do. The first one is convert that into scientific notation. Find out where it starts with a number, then a point, and then another number. So do that first, and then work it out to significant to 3 digits. So step one, scientific. We have to get the decimal point between the first number and the second, the first non-zero. 1, 2, 3. So moving it 3 points to the right, I get 1.5947772 times 10 to the power of. Well, I multiplied this to get that number, didn't I? I moved to the right. So it's not as big as that. It's actually 1,000 times less than that. So that's the answer there. It's 1.59 really, 4 divided by 1,000. So that's why it's the 10 to the minus 3 there. Now, how do I get significant digits? It's saying that I only want 3 of these to matter. I don't have to be that fussy. Well, 3 of them have to matter, so the first one has to matter, the second one has to matter, and the third one has to be correct. So going to the third one, 9,4. Would you round 9,4 up, or would you leave it at 9? 9,4, I think you'd leave it as 9, is that right? By 10 to the minus 3. If that had been 1.597, you'd have to round the 9 up, wouldn't you? And to round the 9 up, you'd have to call it 1.6. So just on that, imagine just the number turned out to be 1.597. How do you round that to 3 decimal places? Well, what did I say? The first number has to be the same, the second number has to be the same, and the third number has to be right. Now, 97 is much nearer 10 than it is 9. 97 is much nearer 100 than it is 90. Isn't that right? So this then would become 100, and it can't be 100 because that would make that 10. So this would make it, well, really it's 1.6. So you'd imagine on the number line you'd have your 1.59, 1.6, and here we have our 1.597. And that will be rounded up there. Whereas the previous one we had, 1.594, was rounded back. So 1.594. So as we saw, 1.594 was rounded to 1.59. But had we chosen a higher number than the 4 there, we would have had to round up. Okay, so last topic of this session. And it's just bringing a few things together. It's the same techniques as before. We're looking at relative and percentage errors. Can I find that? Now, I'm going to do this by going back to a former question. Relative and percentage errors. We're looking at doing a calculation of a conversion in a bank, and we're going to take €1 is 87.87 sterling. We're going to get an answer here. But in sterling or in euro, we're going to be left with either being given sterling notes, possibly sterling coins very rarely, but we're not going to get fractions of them. So there's going to be an error or a rounding in the calculation. We could get it to the nearest £10 note sterling. They might say that's as close as we have. We don't carry individual sterling coins. So that's where an error might come in. So just looking back on the question, we had €1 giving us 87 pence in sterling, and then we were trying to get €40. We worked out the calculation, and we ended up needing €45.98. Actually, it was 45.977. Now, let's imagine that we could actually get it to the nearest penny. we were entitled to hand in 45.977 euro. We don't have 0.977. We only have 0.97 in terms of euro, or do we do 0.98, or how do we do that? So what's the error then? Let's imagine that they only gave it to us in sort of much bigger units like that. 0.977 is our error. How might that appear? Well, 45.977 is the amount of money we need, but they decide to round it down to the nearest euro. Very kind of them to do that, okay? This wouldn't happen, they'd round it up, wouldn't they? But let's imagine we're rounding down. Let's say instead of requiring 45.977, because their commissions are so high, they say, look, just give us the 45. So instead of looking for 45.977, they give us 45. What's the error? Well, what you say there is you say, well, 0.977 is the error out of 45.977. So of the total, which we expected to be 45.977, this was our error. This one became our total. This became our percentage error. So how do we deal with issues like that? Well, it's the same box again. This was our total, 100%. This was our x, if we did it this way. 1 is the total, this is the x. What tiny fraction does 0.977 represent? This is to this, as this is to this. Calculate it again, multiply it across, and we get that x is roughly equal to 0.2125. So the percentage error then is 2.125%. Does that make sense at all? Let's look at that. We were to hand in something like 45 euro, nearly 46. We only handed in 45. The error was 1. 1 euro in 45, which would that be in 100? Which would that be in 90? 1 euro in 45 would be 2 in 90, would it? 2 times 45. And then 2 in 90 would be what in 100? A bit more than 2. So if you're saving a bit of a euro, nearly a full euro, for every 45 you have to spend, how much would you save in the 100? So if this is 100%, what would the percentage be here? If 45.99 represents 100%, what does that represent? So that is to 100 as that is to what? Now if we look at the numbers here, this is about twice that number. This is nearly 1, so about twice that would be 2. You're getting smaller significantly as you go right to left, much bigger as you go left to right. So x turned out to be 2.15%. So basically what we did today is we just used one tabular approach. A box, 2 by 2, 2 by 2, and we used it for virtually everything. We used it for fractions, where 1 is to 3 as 2 is to 6. We used it for conversions of sterling to euro. We used it for ratios, divvying out the stuff. We used it to calculate percentages. And what's a percentage error? Only another percentage. I wanted 45 euro. I got 45 and a bit. What's the difference between them? One is 100%, the other is nearly 100%. What's the gap? You do the crisscross and that's it. So that's it. Gentle start to the session. We'll do another session in a little while. I'm now going to... The trick is now that we're going to go to the canteen, take a break. But the first thing you've got to do is we're going to work out our emergency systems. We're going to check it because we do this. We're going to get